Okay, guys, I promised to give you a proof of that 1/7 triangle, so here it is. On the screen, you see the triangle that I was dealing with. I'm going to go ahead and say that the area of the large triangle, ABC, remember, whenever you see ABC, that's the large outer triangle. The area of ABC is 1. I'm notating it with this little bracket around ABC because I don't want to keep writing area triangle ABC over and over again. The original problem told us that the area of this internal triangle PQR is 1/7 when we've got a 1:2 ratio between the long segment and the short segment of each side. We're going to need a couple of theorems to get started. One of them's pretty obvious, the second one, not at all, which is what made this such a challenging proof. The first theorem we need is that if we have two triangles, they've got different size bases, but they have the same height, they have a common height. If I look at the ratio of the area of those two triangles, the area of the red triangle divided by the area of the blue triangle, it's 1/2 times the base times the height. Written that in the ratio, notice that a lot of things cancel. And so this theorem basically says that if you've got two triangles that have the same height, then the ratio of their areas is equal to the ratio of their bases. All right, that's theorem number 1. Second theorem, you need to look at this red triangle and this blue line that cuts through the red triangle. What we're going to be interested in is looking at how that blue line cuts the sides of this red triangle into pieces. We're eventually going to have a long multiplication that relates all of these pieces, PY, PB, AP, AZ, all of these pieces are going to be related in one large proportion. To show you these proportions, I need to show you some similar triangles. This line I've just drawn in is parallel to BZ, and it goes through this point Y. Since that line is parallel, I've got a couple of similar triangles. That big green one and this smaller orange one, they are similar. So that means I can set up ratios to their corresponding parts. In particular, I can say that PY over AP, the ratio of that piece to the long side, is the same as NZ, this piece, over AZ, that long piece. Those two ratios are equal because these two triangles are similar. Now let's look at two other similar triangles in this drawing. I've got that small one there and a larger one there. The green triangle and the orange triangle are similar. Those triangles are YNC for the orange one, BZC for the green one. Just like above, I can put in corresponding parts of those triangles into a ratio. So CB over YB, this whole piece for the green triangle, over the part that's outside the orange triangle, is equal to ZC over NZ. Now I've got these two ratios that were true for my larger drawing. I'm going to multiply these two ratios together. Once I do, I want you to notice that the NZ's cancel, and I'm left with this expression. If I take this and reciprocate it, I can move it to the other side of the equal sign, and that gives me this large ratio. This is actually a pretty famous theorem. It's called Menelaus theorem, and it simply relates these pieces of the triangle together. I've got a line that cuts through that sort of internal triangle, and this green to this blue times this green to that blue times this green, the whole base, to that blue, are equal to 1. It is by no means obvious, but it sure is handy. It actually shows up a lot when you're trying to show that points are collinear with each other. You've got a drawing and you want to show that 3 points are on the same line. Menelaus theorem shows up a lot. We're not using it for that in our case. Here I'm going to label the triangle to have the ratios that I need. This piece is twice as big as that one. This piece is twice as big as that one. and this piece is twice as big as that one. All right, let's look at the area of this orange triangle that I've got highlighted. If I compare it to the larger triangle ABC, use that first theorem that I showed you. We've got two triangles that have the same height, so I can put the ratio of their areas, the ratio of their bases, equal to each other. So here I've got the triangle AYB, which is the orange triangle, to the ratio of ABC, the large red triangle, is equal to YB over CB. That's the two bases. Now, if I actually plug in values for YB and CB, I can see that YB is 1 and CB is 3, 2 plus 1. So that's where I get this ratio of 1/3 from. So I can actually express the area of that orange triangle, AYB, as 1/3 of the area of the big triangle, ABC. All right, that's important. I'm going to save that ratio and use it again later. I can also plug in values into my ratio from Menelaus theorem. I can plug in values for CB and YB and AZ and ZC. These come straight from this 2, 1, 2, 1. CB is 3, YB is 1, AZ is 2, ZC is 1. So from Menelaus theorem, I can set up this ratio. Now it's just some arithmetic to figure out that PY over AP is equal to 1/6. That's also important, so I'm going to save that ratio up here. Now let's examine the area of this small blue triangle. This is going to be vital to showing the area that we are interested in. I'm going to draw this green triangle in, and I want you to notice I've got another situation where I've got two triangles with a common height. That means that I can put the ratio of the areas and the ratio of the bases equal to each other. That's what I do here. PY over AP. PY, that's the base of the green, over AP, the base of the blue, is equal to the area of PYB, area of the green, divided by area of BPA, area of the blue. PYB I can re-express. If you look at PYB, this green triangle, I can express that as the area of everything that's colored in, both green and blue, minus the blue. Everything colored in minus the blue is PYB. So over here, I'm going to express that. AYB, everything colored in, minus BPA, the blue triangle, is the same as PYB. I can do some algebra here because BPA and BPA are the same thing. I can rewrite that as -1. And I can now notice something from one of the ratios that I saved. AYB is 1/3 of ABC. AYB, this area of everything colored in, is 1/3 of the whole triangle. So I'm going to substitute that in. Some quick algebra moves that 1/3 to the outside of the ratio. Second thing I'm going to use is the other thing I saved. The PY over AP is 1/6. I'm going to substitute 1/6 in for PY over AP. And now I want to solve for the area of this blue triangle right here. Move the 1 over, I get 7/6 equals 1/3, ABC over BPA. So BPA, the area of the blue, is, with just a little bit of algebra, 6/7 times 1/3 of ABC. That is to say that the area of the blue triangle is 2/7 ABC. So if the area of this blue triangle is 2/7 of the area of the entire triangle, I can see that blue triangle in two other places. I could repeat this argument to show you that the area of that orange triangle is also 2/7 of the area of the big triangle, or that the area of this pink triangle is 2/7 of the area of the big triangle. But now that I've got all three of those colored in, and I know that each of them is 2/7, I can add those together to get they total up to be 6/7 of the large triangle. So the area of the remaining piece, triangle PQR in the center, has to be 1/7 of the area of the big triangle. And that proves the theorem. Am I done? Well, I think I still owe you one piece. I gave you a picture in Desmos. After we varied these ratios around, I gave you a curve in Desmos that looked like this. You can see down here that x minus 1 squared over x squared plus x plus 1, that's the formula we found in the last video, where x is the ratio of the sides. In our original triangle, that ratio was 1/2, so that this was 1 for ax, and this was 2, this was 1, this was 2. But we can alter that ratio to be anything we want to get that curve. So I want to show you where this formula comes from, looking at the picture. First of all, I'm going to label the area of the large segments on the sides as m. Before I had labeled it as 2. Let's just say it's something. And that the segments that are short, these segments here, ax, zc, and yb, they are some ratio times m, so xm, x being the ratio of the long segment to the short segment. Now I'm going to try and figure out a ratio with this blue line, a ratio with AP and AY. Well, I can bring Menelaus' theorem back. Since I know that that's equal to 1, I can move these two things to the other side of the equation. They reciprocate when I do that. Now I can plug in values. I know that ZC is equal to XM. Read that off right here. AZ is equal to M. YB is equal to XM. And CB is the whole area down, the whole segment down here, is equal to M plus XM. All right, now it's time for some algebra. Just multiply that out, and I notice that the M squareds cancel. So the ratio of PY over AP, that is the light blue to the dark blue, is x squared over x plus 1. I'm going to take those values, x squared and x plus 1, and move them over to the triangle to label these two segments that I've drawn in. One of them is going to be x squared, and one is going to be x plus 1. Let's move the x squared to be labeling PY, and the x plus 1 to be labeling AP. The ratio of AP over AY, the dark blue piece to the whole thing, AP is x plus 1. The whole thing is x squared plus x plus 1. So that's a nice formula for the ratio of that entire blue segment, the whole thing to the dark piece. Now let's look at the ratio of these two triangles. AP and AY are the bases of those triangles, and they have a common height, just like we saw earlier in the video. So that gives me that AP over AY is the ratio of those two triangles, APB, dark blue triangle, and AYB, everything colored in. I'm going to solve for APB, the dark blue triangle. That was the special 2/7 triangle we saw before. And from some algebra, I can see that it is AP over AY times AYB. Now let's look at the area of this orange triangle. I'm going to use my original theorem again, my ratio of areas when there is a common height. I want to look at the entire triangle ABC and the orange triangle AYB. Because they are two triangles that have a common height, I can set up this ratio. CB times AYB equals YB times the orange triangle, and a little manipulation gives me this. I now notice that I can substitute this expression in for AYB over here. If I take YB over CB times ABC, write it in this spot, I'm going to have something that I'm going to use a little later. Now let's look back at this blue triangle. I see that I have an expression for AP over AY in both of these algebraic things. So I can take this expression and write it here for AP over AY. I can also get measurements for YB and CB off of this triangle. YB is XM, CB is XM plus M. So let's rewrite that ratio over there using x's. From the beginning, I said that the area of triangle ABC is 1. I'm going to use that here. Now let's just do some algebra. The x plus 1's cancel, and I see that the area of this blue triangle is x over x squared plus x plus 1. Well, that blue triangle appears in two other spots. It appears in that orange spot and that pink spot. So the area of PQR, this little middle spot, is 1, the area of the whole triangle, minus 3 of these, minus 3 of the blue triangles, because those colored in triangles are all congruent. So 1 minus 3 of those, some algebra simplifies to this, more algebra simplifies to that, and finally I can factor the numerator. That is the function that we saw in Desmos. It's a long way to go. We got there. I'll see you in the next video.